In this series of videos, we're going to look at control volume analysis. Control volume analysis is one of the most useful concepts in the study of fluid mechanics. At the end of this series of videos, you should be able to understand the distinction between a system and a control volume. You should also be able to select an appropriate control volume to solve problems in fluid mechanics, and apply conservation laws and laws of motion on finite control volumes. So having said that, what is a control volume? A control volume is a region through space through which fluid can flow. That's a simple enough explanation. So that region through space can be real or imaginary. So what do we mean by that? A control volume could be, let's say, your bedroom. So it is a real region through which fluid is flowing. That is a control volume. However, we can also set up imaginary control volumes, and these are regions in space that we delineate ourselves in order to help solve a problem. Furthermore, a control volume can be fixed, or it can be moving, and it can also be rigid or deformable. It's often useful, and dare I say more natural, in experiments to observe a fluid flowing through a region of space instead of following individual particles or sets of particles. So think about, for example, setting up a camera with a fixed viewing field. And we're just going to watch, let's say you set up a camera in a park and you're watching the clouds pass by. It's much more natural to do this when analyzing fluid flows instead of trying to track individual particles. However, we come across a challenge. What is this challenge? Conservation laws, or laws of motion, pertain to systems of matter. That is, they apply to identifiable groups or blobs or particles of matter. So what do we mean by that? Think of Newton's second law. Newton's second law applies to a particle or a group of particles. Okay, so the sum of the forces is equal to the mass times the acceleration. And that mass is an identifiable mass. So think about, let's say, an airplane flying through the sky. It is a fixed, and by fixed I mean it is an identifiable mass that does not appreciably change in time. Of course, there is a change in the mass due to the combustion of the fuel. But what we mean by that is that our conservation laws, such as Newton's second law, is not applied to a region in space, but it's applied to a system. And by a system, we mean an identifiable group of matter or particles. So let's write this out. So conservation laws, and again, so these are conservation of mass, conservation of momentum, etc., or laws of motion, are applied to systems of matter. I.e., they apply to identifiable groups, particles, if we want to say blobs even, of matter. So hopefully this distinction is fairly clear. Okay, so control volume analysis is observing a region in space, real or imaginary. Okay, so that could be a wind tunnel. It could be the flow through an airplane turbofan engine. It could be your bedroom, where you have natural fluid flow process is happening. However, conservation laws, such as conservation of mass, conservation of momentum, they apply to systems of matter. So that is identifiable particles. So the question is here, how do we reconcile our known conservation laws, which apply to specific particles of matter, with our desire to simply observe the flow passing through a region of space? So this will be the focus of this video and the next couple of videos as well. And this is precisely what control volume analysis does. It is a way of reconciling this challenge of our conservation laws being applied to an identifiable particle or group of particles with our desire to just observe a region in space. Okay, let's consider a motivating example. And what we will do, we will look at the simplest case, which is that of conservation of mass. So here what we have in green is some sort of nozzle. Okay, so it's a contraction through which a fluid will pass by. And what I have here in yellow is the control volume. So this is over here in yellow. This is our control volume, which is fixed. And again, what we want to do is look at conservation of mass, and conservation of mass is applied to a group of particles. Okay, so let's assume that we have a group of particles that is identified by the red outline. So the red outline is this one over here. Okay, so as we can see, we have a group of particles that is passing through this nozzle, this contraction. So this system of particles is in red, and we can apply conservation of mass to this group of particles. And so what we have here is that at time t1, the system defined by red and the CV, the control volume, defined in yellow, they overlap with each other. Okay? But at a short time delta t after t1, the system of particles defined in red has moved to the right, as shown in this schematic over here. So at this time delta t after t1, we will have a certain amount of volume that was previously occupied by the system, which is still in the CV, but the system is no longer there. And that is defined by this V in over here. And note that I'm using these special V's here with a line passing through it. And this is to distinguish it from this V here, where this is for a volume and this is for a velocity. Okay, so we have a velocity in and out of our control volume, and that's just with a normal V. But we also have volumes defined by this V with a line passing through it. All right, so a reasonable conservation law for conservation of mass would be something like the time rate of change of the mass in our system, which is defined by the red outline, is 0. dm by dt is 0. So this makes sense. You know, we can neither create nor destroy mass. We have an identifiable group of particles, and we're going to say that as time passes, this group of particles' mass will remain constant. And we're going to use the subscript little m here. And this is to say that this is a material system. And this is a terminology that we use to say that this has to do with a real amount of identifiable particles. Okay. We're going to define a few other things as well. So we're going to say that the mass inside the control volume is the mass in the CV. So mCV is mass in the CV. And we can define it as the integral over the entire control volume of all the little differential masses that we have. So it's essentially a summation of all our differential masses. And recall that the mass is equal to the density multiplied by the volume. So again, I'm using this V with the strike through line to distinguish it from the velocity. We can also say that the mass inside, or rather the mass of our system in red at time t1 is equal to the mass, so rho dV, over volume 1, which is essentially our control volume. Okay, so I have volume 1 over here, and this volume 1 is the volume of the control volume. Okay, so what we can say is, so at time t1, the system is coincident with the CV. Okay, so what we're saying here is that our red outline overlaps with the yellow outline. So the mass and the CV occupy, the system defined in red and the CV defined in yellow, they overlap with each other. So what we can say mathematically is the mass of our system is equal to the mass inside our control volume at time t1. So again, what we're showing here in this schematic is that the system in red passes through the CV, and thus there is a change at time t2. Over a short period delta t, some of the mass has flowed to the right, and so we can define this displacement as delta x in, and some out of the CV, which we define as delta x out. So mathematically, what we can say is that the mass of our system, which we define as mm, is equal to the mass of the CV. Okay, so this is the mass calculated over volume 1, and volume 1 is essentially the mass, the volume of the CV. So that's at time t1, and again, that mass is not going to change with time. Okay, we can define this as well as, so this side and the right hand side will be equivalent. Okay, we can also define this as the mass inside the CV at a given time minus the amount of mass that moves to the right, and this is this volume here on the left hand side, and then plus the amount of mass that sorry, I should be careful with my integrations here. This here would be our volume V in, and this will be our volume V out, and so that's the amount of mass that has exited the CV over that short period of time, delta t. Okay, so for a short delta t, we can say that delta x in So the amount of displacement is equal to v in, our velocity inward, multiplied by delta t. So I'd invite you to pause here and think of what assumption has been made in saying in this expression over here. So what assumption are we making about the velocity v in? What we're saying here is that v in is constant at this entire face over here. Okay, so what we're saying is that there's no velocity profile, meaning that, maybe the velocity is, smaller near the walls and larger near the center over here. So what this is saying is that this is constant across the surface. Okay, so it would look something like this is what we call a top hat profile. So it's a constant velocity, v in. Okay. We can also define the volume at the inlet that has moved to the right as the area of the inlet of our CV multiplied by delta x in, which we have just defined. And so this tells us that we have A in multiplied by V in delta t. Okay, and we can shrink this to an elemental volume. So we can say that our differential volume is equal to dA dx, and that is equal to V in dA dt. And this is all coming from here with certain parameters shrunk to their differential sizes. Okay. So what this gives us is that the mass that has passed through V in will be equal to rho V in dA dt. And again, this would be a double integral, 1 over the area and 1 over time. Okay, and again, this term here is our dV, which is coming from over here. Okay, let's pause for a second and think about what we're doing. Okay, so we've identified a system, which is an identifiable group of particles, which we have denoted by the red outline in our schematic. And what we're saying is a conservation of mass would tell us that dm by dt, the time rate of change of that identifiable group of particles, will not change with time. At time t1, the system overlaps with the volume of the CV. And this is what we are saying right over here. Now, the overall mass of the system is equal to the mass at time t1, which is the mass of volume 1, which is the mass of the CV. Okay? But we can also describe it at time t2 as the mass within the CV minus the mass that was previously occupied in the volume defined by V in, plus the mass that is occupied by the volume V out. Okay? And then what we've done here is that we are just defining these differential variables here, dV, for the differential volume. Okay? So if we call this equation 1, equation 1 becomes, okay, so the mass is equal to the mass within volume 1 at time 1, which is the volume of the CV, but it is also equal to the mass inside the CV, the control volume, at time t2, okay, minus the mass that has passed through the volume V in plus the mass that has passed through the volume V out. And the area corresponding to V out, volume out, is A out. And the area corresponding to volume in is A in. And again, these V in and V out are actually velocities. Okay? So again, conservation of mass would tell us that the time rate of change of the mass of the system is equal to 0. So we can take the time rate of change of equation 1 and set that equal to 0. And this is precisely what we're going to do. So we have dm by dt is equal to 0 is equal to d by dt of the mass inside the CV at a given time t minus d by dt of our integral over A in, the area of the inlet, rho V in dA dt, plus the time rate of change, and that now is applied at the outlet. And as we can see, so the differential area is not going to change. We're assuming that the density is not changing with time either. So all of this is going to simplify quite nicely. And what we're going to get is, for our conservation of mass, is d by dt of the mass inside the CV minus the integral of rho V in dA plus rho V out dA, and that is over A out, the area of the outlet. And here we are. This is our conservation of mass applied to a control volume. So this is a control volume expression for the conservation of mass, which is also known as continuity. Continuity, or conservation of mass. Okay, so what this says, for conservation of mass, if we're observing a, let's say, a fixed CV, so let's say a room that is not changing with time, okay, then the time rate of change of the mass inside the control volume, so let's say it is the room, is equal to, and so if we were to rearrange this, so this time rate of change, so as the time rate of change of the mass inside of a room, is equal to the amount of mass coming in minus the amount of mass coming out. And this kind of makes sense, intuitively. And we're going to look at the implications of this equation much more deeply in the upcoming videos.